Great. Thanks for the reminder. Clicker, left and right.
Good morning, all. I'm Greg Frankenfeld. I work for Mackey Mitchell Architects in St. Louis. We're headquartered in St. Louis. We have an office in Asheville, North Carolina, Lawrence, Kansas, and a brand new office in Dallas, Texas, and I'm currently in the middle of my move to Dallas as I'm speaking right now. My car is loaded, my cat's at the hotel room, and I'm making this transition now, and I thought I'd stop in and just talk a little bit about a recent project. So Mackey Mitchell has been in business now. We just celebrated 50 years last year, and we do a lot of student life, a lot of residence halls. We do a mix of things, but great place to work, and I've been there for 12 years. And I'd like to let Rob introduce himself now.
Yeah, thank you. Rob Dobb with Napholz Construction. I'm the EVP of Operations in our Northwest Arkansas division. I've been with Napholz 12 years myself. Spent 21 years in the design profession, structural engineering and architecture before joining Napholz back in 2007. A little bit about Napholz. We're a 70-year-old company founded in 1949. We've got about 1,250 people that work for us, do just right at $1 billion a year right now. So we haven't hit the billion yet, but we're right there. We have offices, main offices in Conway, Little Rock. That's where our headquarters is, and then Rogers, Arkansas, where I'm at, and then Kansas City. We have an office in Springfield, Jonesboro, Memphis. Just opened a service operation in Nashville, Oklahoma City, and Tulsa and Fort Smith. We also just recently opened an office in Connecticut to serve the rail yard industry, so part of our industrial services division. We do a lot of K-12 and higher ed work. It's about 40% of our annual volume, and we're the number 10 nationally ranked construction manager in the K-12 industry, and number 19 overall. So a little bit about our company.
I neglected to mention that I'm an alum here. I graduated from Drury in 1991. So don't worry about doing the math. I don't want to get into that. But so we're here again to talk about Adohi Residence Hall at the University of Arkansas in Fayetteville. This project started in 2016, and up until just a few months ago, it was Stadium Drive Residence Hall. So if you hear me refer to this, or Rob refer to this as Stadium Drive Res Hall, that's why, because that's what we've been calling it in all of our correspondence and all of our meetings over the last few years. So just a couple of, I also did want to mention that you also saw a photo of Chris Baribeau. He's with Moda Studio in Fayetteville. I got down here last night, checked into my hotel room, and was looking at the presentation just to make sure everything was in order, and I checked my email, and Chris couldn't make it at the last minute, so had to scramble a little bit to kind of pull some additional thoughts together on the presentation, but sorry he couldn't make it, so it's just Rob and I. Just a couple of highlights of the building. The Res Hall was largest mass timber residence in the United States, 202,000 square feet, over 700 beds with a mix of traditional and semi-suite bedroom units. We'll get in, I'll show a little bit more of that later. It's referred to as a mass timber building, but in reality it's a hybrid building. I mean, really, there aren't many mass timber projects that are fully mass timber. You're going to have concrete come for your foundations, and you might need some steel to help for structural reasons. So we'll talk a little bit more about that as well. But primarily we use cross-laminated timber, CLT, for our roof and our wall and our floor panels, and then glue lam columns and beams. Just a shot of everybody that worked on the project. One of the unique things about this project was it was a really large team. you see three architects. So Mackie Mitchell was, we were brought on the team as the student life expert, student housing expert. Moda Studio was the local architect of record, and Lairs Weinzapfel Architects had some experience in mass timber. So, and then also, it's kind of unusual, we had two structural engineers on the project as well. The local engineering consultants did primarily concrete and steel design, and Equilibrium has a expertise in mass timber, so that's why they were on the team. So kind of what we want to cover today, we want to talk a little about what is mass timber. Not going to dig too deep into it. It's a subject that we could talk about for a few hours probably, but I'm going to kind of keep it at a high level. I'm happy to answer some questions afterwards if we want to get into the weeds a little bit more. Talk about why the University of Arkansas chose mass timber for this project. We want to explain the design process and how mass timber impacted that, and then we'll talk about a little bit about the construction and lessons learned. So what is mass timber? When we think about wood construction, this is probably the first thing that comes to mind. This, probably the predominant use of wood is light frame construction and residential work. We step back a little bit. Heavy timber. This is a photo from the Couples buildings in St. Louis, where our office is at Mackie Mitchell. This is from these were built around the 1890s. And then if we go way back, the oldest wood building in the world is this temple in Japan, built in between 600 and 800 AD. So any myth about wood and its longevity, here's proof that if it's designed right, detailed right, it can last a really long time. This is from, I think, the 15th century in Germany, showing some half timber structures. And then, of course, as we move forward into the boom of concrete and steel and the skyscraper age, and then this is the result of that. And hate to think of what the carbon footprint for Hong Kong is, but kind of leads us into a little bit about one of the great things about using wood is it's renewable and it has great environmental benefits. So you might hear mass timber referred to as advanced timber or engineered wood. Essentially, it's combining, the concept is combining smaller dimensional lumber and combining it in a way to make larger panels. Probably the earliest example of an engineered wood is plywood. And that's been around for quite a while, but the idea of taking veneers and perpendicularly laminating them together, and it achieves great strength. Glulam's been around, and first use of glulam in the U.S. is probably about 80 years or so. So here's a photo of some glulam under fabrication and just an example shot. Many of us have probably worked on projects with glulam. And so here are some fabrication shots of CLT panels. So CLT is generally between 3 to 7 plies, depending on the span needs and the strength of the material. But again, it kind of shows the perpendicular layering of dimensional lumber that gets glued and then pressed. Here's the family of most of the mass timber products that are available. Again, on Arkansas, I'm most familiar with CLT and glulam. I haven't used any of these other products. So as I mentioned already, there's some great environmental benefits, of course, and we could go down a rabbit hole and talk about that, but that's not what I really want to spend a lot of time talking about. The idea of biophilia, which is defined as the love of life or living systems, and the innate nature of humans and drawn to living things. Their health and well-being benefits to wood. Ease of fabrication, wood's a soft product, it's easily manipulated. Rob probably touch a little bit about speed of construction. And one of the things that's kind of has helped advance this technology is, HJs and other code officials are catching on to really the capabilities of wood. That there are a lot of myths about why wood isn't maybe the best material to use depending on the project, because it's combustible. It doesn't mix well with water sometimes. There are a lot of reasons. It's not as strong maybe, but in reality, it is very strong when you think about the portion of the strength to weight ratio. But it's really become, just being involved with this project, and Rob can attest to this too. I mean, we get calls all the time to talk and to ask questions and be on teams to pursue work, because it's really a hot topic and a very trending, popular construction type that's gaining a lot of momentum right now. So it was really just a great project to be involved with. And these CLT panels are been a big part of why there's this new boom in mass timber. And these panels now can be made up to up greater than 10 feet wide, 10 up to maybe 12. And up to about 60 feet long. Really, the limiting factor more than anything is just how you're going to get it to a job site, how you're going to ship it. So they're in a plant. They go through these. They use these these CNC machines, and you can get very very detailed, and tolerances are within fractions of an inch, which is great that you can do this in a controlled setting of a factory, and it solves some of the problems at the job site. This is a slide just from Woodworks that illustrates and talks to just the increase in this construction type. I was at the International Mass Timber Conference last year in Portland, and their stats were that annually the quantity of mass timber projects is doubling every year. And that's probably just going to continue to increase. But this is an interesting chart to look at, state by state, how many projects are in development or under construction or complete. So the United States is really kind of catching up to everybody else. This is Europe and Canada. It started in Europe, and Canada's got a lot of work with mass timber, and now the United States is trying to catch up. But there's just a lot of unknowns. Like, most of the construction industry doesn't know a lot about what it takes to make one of these projects successful. Rob's going to talk a little bit about that. Interesting, just some examples of mass timber in place. This is at the University of Arkansas with the glulam columns and beams and with CLT shear wall panels. This is Vancouver, load-bearing CLT shear walls. We even use them for stair towers, rated stair enclosures. This is at Amherst, UMass. This is a project by Lears Weinzapfel. Same project, showing them setting some floor panels, and what you're looking at is they can, typically you're going to put a topping layer on top of a CLT panel, because wood's not going to be a good material for your finished floor, or to take adhesives for whatever your finished floor might be. So you're going to use a topping. Typically at Arkansas we use 1.5 inches of a gypsum topping. We didn't need a composite slab there. But this was an example of where they ended up using a lightweight concrete in a composite system, where those are steel fins that are embedded into the CLT, and when the concrete forms around it, it forms a composite system. And then we use them for roof panels as well. So talking a little bit about the project that we came to explain, everybody knows probably where Fayetteville is in northwest Arkansas. We're only a couple hours away from it here. So the state of Arkansas, amazingly, has 4.7 million acres of certified forests. And so that is part of the interest and the reason why the university wanted to pursue that. Dean Peter McKeith at the School of Architecture sent some information to me. I'm going to read it. This speaks to kind of what their motives were for pursuing this building. Advanced Timber Technologies, or more simply mass timber, appealed to the University of Arkansas on this project for its triple bottom line deliverables of demonstrable educational value, demonstrable environmental value, and demonstrable economic value. The Dohe Hall is not the first mass timber campus facility at the U of A. That distinction belongs to the Library Annex building, which is the photo I showed you of the example, which was dedicated in the fall of 2018, nor will it be the university's last mass timber building. There are at least 2 more envisioned in the next 5 years. But it is the first to be so explicitly specified in the RFQ, the largest mass timber campus building constructed to date, and the one most greatly anticipated, given the scale of the budget, the prominence of the site, its multi-story height, and the diversity of its program. Mass timber appealed to the university and its design, engineering, and contracting partners for this project for its simplicity and speed of construction, its versatility in both short and long span conditions, and its psychological and physiological effect on the interior quality of the spaces. The promotional value of the project should not be underestimated either, as the project signals a university committed to progressive design and innovation, to sustainable design, and to a vital quality of on-campus residency. So when we started this project and we were filtering through the RFQ, as he mentioned, it wasn't a for sure thing this project was going to move forward as mass timber. And we carried studies for more traditional steel frame building alongside a mass timber building all the way through, longer than we should have in the design phase. It kind of put us behind the pickle a little bit when they finally did make a decision, had the funding in place for us to meet their schedule. And we'll talk a little bit more about that later. But quickly, for anybody that doesn't know the university, so north is to the right, the kind of the main part of campus, and our building is right off of Stadium Drive, right next to Bud Walton Arena. There's another aerial view from the south looking north. You can see it circled where our site is. From north to south, the site sloped about 15 feet. Of course, Arkansas is a beautiful state, and the Ozarks are a tremendous asset. One of the common themes of our project was a cabin in the woods. And so in our early planning stages for the building, mentioned earlier that we had a mix of semi-suite units and traditional bedroom units. This isn't the actual unit that we ended up with, it's just one of our design images, but so taking that out, double-loaded corridor, these bedroom units become so important in residence halls and the efficiency of them, because when you're repeating these units, times 100 or times 200, just a few inches here or there makes a significant impact on square footage and cost of the building. So, one of our early focuses is always to be very efficient with our planning. And so the most efficient layout for a residence hall is typically a double-loaded corridor. So you create these bars. How mass timber factored into kind of how we laid out our typical units was we established an 8-foot by 40-foot as an ideal CLT size for our floor panels. So that worked with the grid spacing that we're showing here, 12-foot demising wall center to center between bedrooms, and then a 40-foot wide building for the CLT panel. Now, there are some manufacturers that had the capacity, even back when this was built, to make them a little bit bigger, maybe 9 or 10 feet. Now I said you can get them even a little bit bigger and even a little bit longer now. But we didn't want to rule anybody out, and we wanted to make sure we had competitive bidding, so we picked a common size that we knew a lot of the fabricators could provide and bid on. So this module worked out great for our traditional bedroom wing, which this is what we call our pod wing that utilize community bathrooms. So with three 8-foot wide panels by 40 feet, very efficient, not a lot of waste, not a lot of cutting. And then how that played out on the semi-suite wing is, because the building's a little bit wider, because you have the bathrooms at every bedroom unit, we had it set up so that we'd use a full 40-foot panel, and then we could, cut a full panel in half and utilize it on the other side of the building. So a very efficient way and very thoughtful from the very early stages of this building. And regardless if this building was going to be steel or mass timber, this was going to be our grid spacing. So we carried this through even with our steel concept as well. Just showing you some early, some design images of how the project evolved, and we decided based on the linear nature of the site, the slope, the quantity of beds, that it made sense to kind of split it up into two buildings. So the north building was called Building A, south building was called Building B. We had some, is this a pointer thing? Yeah, so here's the basketball arena. And currently on site, there is a series of, there's what they called an oak grove. One of the priorities was to maintain as much of the trees as we could. And then we came up with a connector piece that we called the bridge to connect both the A building and the B building. One of the interesting things about the configuration of what we end up calling this is a serpentine scheme. We had several schemes that we looked at, but this is the loading dock for Bud Walton Arena, where the semi-trucks have to service the building for deliveries. And our site obviously is buttoned right up against that drive. So the shape of our building had to take into consideration that the semis have to have turning radius and back up. So we factored that into our design. Just a little bit of a blow up of it. Pomfret, which is next door, is another residence hall. They hadn't built a residence hall, and this is the first residence hall in 15 years at the university. So, along with being a residence hall, this was intended to be a living, learning community as well. So, in the south building, the B building, these spaces were designed for the arts, and so we've incorporated some maker spaces, faculty offices, there's music rooms, there's some video production and audio production studios, and then there's like a movement studio or dance studio, and then there's a really nice kind of a tiered seating with a high volume amphitheater space here. And in the north building, here's the main building to the residence hall, so this is where the students will enter. And then the cabin, the connecting building, is only a one-story building, which is kind of the social heart of the building where everybody comes together, very transparent. Typical residential floor, again, I mentioned we've got the wider wings are the double semi-suites, the more narrow wings are the pod wings. Here's an axon of a cutaway of that first level, showing the makerspace and arts department with this tiered amphitheater. Here's the cabin, the social, kind of the living room, and then the first floor of the res hall. And of course, here's an illustration of the glue-lam post and beam structural system. And then we layer on our CLT floor and roof panels, and then ultimately one of the final renderings of the completed design. And the university was a little bit leery about, one of the hesitations for using mass timber was I don't know about, we're not familiar with it. We're worried about it. It's flammable, all those things that a lot of people are concerned about. So ultimately, we didn't even pursue using CLT for any of our shear walls. So all of our elevator and stair towers are poured in place concrete. They also didn't like the idea of exposing any wood to the exterior for maintenance reasons, understandable. There is a little bit of wood on soffit conditions. You'll see some photos, but the building is skinned with metal panel. And we tried to, because this is, part of this is promoting mass timber and the Arkansas forest industry. We wanted to highlight, and so you'll see in some photos later that wherever we could, we tried to capture large glass windows that had a lot of exposed wood that you could see from the outside. So even though we didn't use a lot of wood on the outside of the building, on the inside there is a lot, and we wanted to make that visible. And so one of the key things was, trying to condense all of our utilities, our systems, MEP, FP, telecom, sprinkler piping. As much as we could, we tried to condense that down the corridors so that we could maintain a really nice volume in the exposed CLT floor panel, along with the glue lam columns and beams in the bedrooms. A long way from Turner Hall here at Drury, which was my first residence hall. Another shot of just one of the final renderings of the project. Now I'm going to let Rob step in and talk a little bit about construction and lessons learned.
Thank you. That's a great job. I know a lot of you were maybe at the White River Conference Center about a year ago when we did a presentation on this project during construction. So, and I had to fill in and do Greg's part that he just did. So that was a whole lot better than I did it. So this was a real collaborative effort, and it requires this type of construction does require collaboration. We got together with the design teams, the owner, the user groups, and took a trip to Vancouver early on. And like Greg said, there was a lot of even a little bit of opposition, but a little bit of just uneasiness about the unknown of using wood. And so a lot of people had to go and kind of lay eyes on it and be convinced. And one thing that really struck me when I was in Vancouver, we went and saw several facilities, and a lot of them, the wood was real prominent and was featured and exposed. But what struck me was the number of facilities that we went in that were complete, CLT and wood mass timber structures that you didn't even see the wood. I mean, they were completely, everything was concealed. We went like the 5th largest Ronald McDonald House in the world that was there. And everything, the walls, the roof panels, everything was CLT, and you saw none of it. And that told me that the wood was being used, for its efficiency as a structure. It's just another viable structural option, for a building. Because you can understand people wanting to use wood to expose it for its beauty and its warmth, even if you had to pay for it. But if you're hiding it in the walls and using it as a structural system, it's a viable alternative for a structure as well. And I think that's what you're going to see more and more of here in coming years. Some of the advantages of mass timber, the precision that, and Greg talked about the tolerance, it really is fast, it really is quiet, and it really is clean. You have to take, some things have to be accounted for, for this speed of construction, but these things all do come into play. And with the precision, that tolerance, I'll talk a little bit about it more in a minute with some of the lessons learned. But the wood-to-wood tolerances, I mean, they're just spot on. They're like everything's within a 1/16 of an inch. And, it was amazing how well everything went together, especially in the wood-to-wood condition. There you got to coordinate very well on the front end. I'll get into that a little bit more going forward. This is a little illustration of you know, when in the wood, we, at the CD phase, we did introduce the timber package and brought on the timber fabricator. Honestly, it would work best if that was done back here. Everything on this job, and Greg mentioned it, that this job was designed with two different systems. It could have gone structural steel or wood up until right in here. And it was a condensed design time frame anyway. And then when the trigger wasn't pulled until here to move forward, there just wasn't a lot of time left to do everything that needed to be done the most efficient way. So, and I'll talk about some of the lessons learned because of that coming up here. This is, I want to start off here, and I've got a couple of time-lapse videos, and this is, this will show, this will really illustrate all the work that goes on for about 6 months while we were getting ready for the timber to arrive on site. And what will be striking in this video is how much happens, and once a timber arrives, how quick that timber goes in place. See a lot of the concrete stair cores going up that Greg mentioned. Now the timber's arriving and going up. And you can see as soon as that timber goes up, I mean, you're skinning right behind it too. So that was kind of early on in the job, but I think that's real striking to show, you know, how quick things happen once a timber arrives on site. Greg mentioned the logistics of this job. It was really challenging. As mentioned, this Bud Walton Arena with the loading dock right here. One of the earlier photos showed this street coming through right here, and it used to continue. This was the truck route right through right here. And not only did the street run through here, there was a lot of fiber optics and gas lines and all kinds of spaghetti network of utilities that were underneath here. So a lot of that had to be moved before we started. There was a deep excavation in the basement right here. Another unique structural system on this job was the use of rammed aggregate piers as a soil stabilizer. And I think they had 1,100 and something rammed aggregate piers on this job. But we had to shore, this had 18 wheelers coming in just a few feet away from our about 24-foot deep basement excavation that happened right along this wall right here that we had to engineer and shore up. And like Greg mentioned, the trucks came in here 2 or 3 times a week throughout construction. I mean, we never had a time where we had to keep this open at all times. There was either basketball season or concerts or something going on there all the time in Bud Walton Arena. So that was a real challenge, and that also got into some of the efficiencies of, you know, if we could set up a self-erect tower crane, and you know, there were some things that we couldn't do because of having this area. Luckily, we had this yard across the street right here where we could bring trucks in and unload, and I'll show some photos of that here in a minute, and then truck them across the street for the day's work and put them in place. Not ideal, but it worked out pretty efficiently. It wasn't as ideal as being able to pull trucks in and pluck them off the back of the trucks and set them in place. But it worked out all right. Here's some of that I mentioned, some of the yard storage and the transport. When these trucks came in, we had this material sourced in Austria. When we had 5 fabricators that we invited to participate, and when we got the timber package available to go out to bid, we had a competitive process between 5 fabricators. 2 of them were in Europe, Vinderholz and KLH, and then we had Smart Lam out of Vancouver, Structure Lam out of Vancouver, Smart Lam out of they were out of Canada and partnered with Western Arts Ribbon and D.R. Johnson. So we had 5 that we invited, and they bid on. We had a timber package that was again, it was like about a 60% DD phase that we tried to bring them in, and that the thought behind that was to allow all the design to be finished with the manufacturer that was going to actually be on the job, so that everything would be detailed to the way that they did things. Some of that worked out. Some of it, the timing wasn't great, but that was the intent. And we ended up with bender holes out of Austria. So this was Austrian spruce. Greg pointed out the pain that they went to lay out these all the suites on 12-foot. We use them 8-foot panels on 12-foot centers for the structure. Bender holes, the panels that they made, they were called a BBS 425, and a 425 is the 4.25 meters, and so they were. It wasn't four. It was BBS 125, which is 1.25 meters, which is like 4 foot 3 inches. So instead of 8-foot panels, we had 4 foot 3 wide panels. There's pros and cons there. They were lighter and easier to handle, but there was double the number of splines. And CLT creates a diaphragm by you set the panels side by side, and they have a spline groove. It's a 1/2 inch deep by 3 inches wide, and you butt them together. So that 3 inch wide on both panels makes a 6 inch wide spline groove that they put adhesive and screws and a strip of plywood in that 6 inch spline, and screw them together and connect the panels that way. So we had twice as much of that to do as we would have if they were 8-foot panels. But they did go in quicker, so it kind of offsets there. This was a really neat device that that Better Holtz provided. They screwed this into the end of a salvage panel. There's some neat stories behind these salvage panels as well. They used a lot of those to make some of the furniture that's in the building, and you'll see in the final photos here in a minute, and it's really cool. There was also, do you know the story about this being sent to New York and used in that village?
No.
Something that there was some kind of collaboration with the University of Arkansas, and there's a story on it. You can look it up, but some of these panels that were dunnage panels that everything was shipped over on was actually sent to somebody in New York, and there's some kind of little small enclave that was built with a lot, structure that was built with a lot of these dunnage panels there. So, I mean, nothing went to waste. But these were screwed into the end of the dunnage panel and then just loaded off the trucks. And we had 125 shipping containers that came over from Austria and to a port in Houston. And then J.B. Hunt Transport, which is a local trucking company there in northwest Arkansas, we arranged for them to pick these loads up at the port in Houston and transport them to site. And they gave us 45 minutes to bring them on the site and get them unloaded and sent back. So we had to sequence everything, the right panels and the right containers at the right time, and bring them in, and had to be real efficient to get these things in and unload them. And we only had room for about 4 of these on site at any time, so we had to be real good about getting these things unloaded. These are some knife plates. This will come up this is a lessons learned thing right here too. You can see that a whole lot went into some of the connections. Some of these connections had like 300 screws in a single connection, and there was 2,500 connections on this job. And these connections, some of them can be done in the shop. That's an efficient way to do it, but it's not an efficient way to ship them. You know, if they can't pack it, all these knife plates and connection plates are connected to columns and beams at the shop. They can't load them into the containers efficiently. So the first 4 or 5 containers that we received on site were nothing but these plates and screws. And then we set up a small army and a whole lot of PLT screw guns and a whole lot of worn out elbows, and set up an assembly line and connected all these things as they were being shipped in. There's a connection to a round column. There were several round columns on this job. Here's an early shot of it going up. here's all these splines that I was talking about. Again, they're every 4 foot 3 inches on the center. One of the challenges that's a little bit different when you're working with structure as a finished material. Usually when you're throwing up steel and pouring concrete, you're not worried about the structure. In this case, I mean, as soon as that structure was coming in, I mean, there was an immediate need to protect it, both from just the rough construction nature of lifts and everything that happens on the job, plus exposure to rain. You can see some of the steps that we took right here. All these columns that went up 4 foot high. We encased all the bases with plywood up 4 feet high to keep these things from getting damaged during construction. Everything was raised up off the concrete 4 inches. They had bases, and there's a detail of that coming up here in a minute. You see, we had a little bit of this on the job, very, very minor. A lot of that, and some of the places that this occurred was in areas that right along the edges that had walls and were concealed by sheetrock later on anyway. Honestly, we had very, very little staining that we had to deal with on the job. You can see some of the steps that we took right here to protect where columns went through the floor. We sealed those up. We taped all that. This tape was not necessary, for the system. But once we put the adhesive down and the screws, we also went right behind it immediately and taped all the joints. And it worked really well. This is, that right there is right on top of that, and that is the exposed ceiling in all dorm rooms. So that's going to be your weak spot. If any moisture is on there, it's going down through that joint. So we had to protect that. Again, here's the spline connections. The penetrations, part of the collaboration, there was 3,768 holes that were 3 inches or larger that were drilled in the shop in Austria before these were shipped over. So if you let that sink in, think of the work that had to be done on the front end and all the design that had to be completed to know exactly where 3,768 holes, the size of the holes, the size of the insulation that went around the holes, and the angular space, and knowing exactly where everything went, and put it in a 3D model, and get all that done for 202,000 square feet before you pull the trigger and send these panels into the shop. So that's where the collaboration on the front end is key.
And the shop drawings were quite an experience.
Yeah.
Not to mention it was metric too, so.
Yeah. So, and you can count, I mean, I think there was probably less than 10 on the whole job where holes had to be either plugged or re-drilled. And it was probably I think in each case, it wasn't a misdrill, but it was a change in a room configuration or something. And that was easily handled as well. It blew my mind. I would have never guessed that with 4,000 penetrations being drilled in 4 foot 3 panels, being shipped across the ocean and put in place, that you would have that kind of precision. But it was. They were spot on, every one of them. And this is a good example of, everything. You can see all the penetrations everywhere here. Cool thing too is that, once these shop drawings were done, I mean, all this stuff right here, it was amazing when the glue lamps went up, the panels were set on place, they were right behind it with pipe and hanging up, because it had all been fabricated in the shop already. Everybody, you already knew where everything was. Another lesson learned thing, we were approached by Vanderbilts for shipping purposes, and they kind of sold it as a speed of installation thing as well to do multi-story columns. Typically, when you're doing the mass timber, they go up floor by floor, and And we learned the hard way why that's a really good thing to do. This seemed like a good idea, but it really got us back into a steel erection, methodology. And it was really hard to, some of these splices, a couple of things happened. The splices in these columns occurred within the floor plane. So that meant that the floor, where at the elevation of the splice could not be in place, until the next column was set and the splice was finished. And so in a lot of cases, we had 4 and 5 story columns, a 2-story and a 3-story that came together, and the only floor that we had to work off of was the first one. And because the splice occurred at floor 2, but then we had columns going up another 3 floors and had the splice, and so we had to apply an elaborate scheme of bracing these tall columns, while we were getting the rest of the floor plates off there, instead of something real simple of working, put the floor and working on the next floor off of that deck. So it seemed like it seemed like there were some good points to it, but in the end, that's something we would definitely do different. Yeah, you can see an example of that right here. That was a real challenge. Again, I mentioned the structure as a field, as a finished material. We had to do some notching on some panels on the corners because of these multi-story columns, and setting them in there. We had some cutouts that we had to come back in and pull back in later. You can see the challenge of setting something. If that's not left out and this corner's not left out, you can't physically drop that in and get it in place. So we had to come back and do some things there. Kind of shows that. Greg mentioned this, and it's good. It's worth pointing out. This was a big timber job. I think just the purchase order for the timber alone was about $5.5 million. But even with all that timber, and then that was the purchase order for the timber. We actually self-performed the installation of the timber on this job too, in-house. And the cool thing is, we've done some steel erection in the past, and we had, got a good carpentry crew. And we sent teams out and saw some of this happening out in Portland, and decided to take it on. It really wasn't that frightening, and it worked out pretty well. I think we would do it again. We are doing it again right now. So it goes together really quick with a good lead person and a good crane operator, and then just skilled carpenters. And but the coordination between the other structural items, even with all that wood, we still had like a $6 million concrete package on this job, and we had a $2 million structural steel package. And you don't see much structural steel in this. There was, some of the large spans and stuff that go in here, but that's where the the devil was in the details right there, because the tight tolerances, the wood-to-wood stuff. It's all the shop drawings, and it's all designed and detailed to go together and fit like a glove. But the tolerances between, just the tolerance that's allowed, AISC tolerances in the steel and the AIC tolerances in concrete don't work well with the type tolerances of wood. So anytime wood abutted concrete, we had to come up with some adjustable type anchors, and that was a challenge. Here's one of the base plates. You see how heavy they are. This went on the bottom of the glue lamp columns, and then connected to this was like a regular structural steel column base plate connection, anchor bolts at its base, and then elevated this up through the column block out above the floor. You see what that detail looks like. Could have shown you a cleaner picture of a column block out there. Yeah, that's that's a critical detail for wood to keep it off the concrete. And here's some of the coordination that we had to deal with, abutting. We had, these steel knife plates that welded the embed plates that was in the, concrete stair towers that were 5 stories tall. And you get concrete within a ½ inch on 5 stories, and you've got a perfect wall, but it is not near perfect enough for a 16-inch tolerance on wood. So this right here was we had to figure out a way to make this adjustable. We actually have I mentioned our industrial service. We have a shop that fabricates specialty iron and structural steel shapes, and they actually came up with a jig that they engineered and built for us that we brought out to do this when we had this condition. Because these rods were driven in a precise location, so this very, very little adjustability on something right here that needed some adjustment. All right, this is the first time-lapse video. The camera was over here looking back this way. This one is on top of Pomfret Hall. This camera is going to be sitting on top of Pomfret Hall that Greg pointed out to you earlier looking, and this is more toward the end of construction. Pretty cool, and like I said, as soon as the wood goes up, everything's coming along behind it, and you can close it in and start hanging right behind it. So, a couple of cool little facts to point out on this. This is a really large building, no matter what kind of building it is, 200,000 square feet. A lot of wood goes in this building. There was about 145,000 cubic feet of wood, and I think 110,000 cubic feet of that was in the CLT panels, and 35,000 of it was in the glulam columns and beams. The wood made up about 184,000 square feet of floor area. So, you see the mass of the building, and with those kind of numbers, 145,000 cubic feet of wood. But the cool thing is from a sustainability standpoint, and why this is popular and really gaining momentum. That amount of wood right there is regrown in Arkansas forest alone in about 4 hours. So it's a very sustainable product, and you're never going to run out of material. And that was one of the big pushes with the governor of Arkansas and like Dean McKeith at the University School of Architecture to really promote wood and get this thing going. One of the challenge that we had on this job, and it was a great challenge to have, but we had tours on this job, especially when the wood structure started going up. There were tours on this job about every Thursday and Friday. We were scheduling around, working around. It was great to see people come from all over the country to see what was happening right here, and I can see it taking off. Another really cool fact. The amount of wood that went in this building, when wood sequesters carbon dioxide, and the amount of carbon dioxide that's sequestered in the wood that's in this building is the equivalent of removing 715 vehicles from the roads for a year. So that's a pretty cool fact. Greg, I think.
Just wrap it up with
a couple things. Lesson learned stuff real quick. The upfront coordination. Don't underestimate the amount of time it takes up front, to coordinate this. It pays off, but you got to spend time up front to make it work. Really pay attention to the connections and the details. That's we overcame a lot, but you can really be efficient with connections and details. And again, having the time up front to figure that stuff out so you're not making quick decisions. that you realize a couple weeks later or a couple months later, in hindsight, one of the best decisions to make. The multi-story columns was a big lesson learned, and again, the tolerances with other materials is a big factor. So, I think now, do you have anything else, or are we just going to show them some of the finished slides, or?
Show them the finished slides. Yeah, these are
Yep.
some brand new photos.
Yep. Yeah, we just got these. These are hot off the press, and really shows how impressive the building is.
There's again kind of the idea of as much as we could from the exterior, showing off the wood inside the building. This is that oak grove that I mentioned, and you'll see in another photo coming up here that these pass-throughs under the buildings, you know, we kind of try to carry that theme of more of an organic, kind of a natural, like where we angled the columns to replicate a tree essentially holding up the building.
This wood material that you see exposed on the outside of the building is Arkansas cypress, correct?
Yeah.
It was, yeah.
Yeah.
One of the outdoor amphitheaters. This is the indoor amphitheater seating. Here's some of that dungeon material that they use for seating. I'll show you some more here in a minute. It's one of the areas you were talking about on the corners.
Yeah. There's a connector piece. There's actually, I don't think we have a really good photo, but there's actually a roof garden on top of this connector building as well that has student access. Inside the cabin, again, is the use of cypress, so nothing you see here is actually mass timber CLT, but again, the cabin in the woods, we want to carry that theme through and expose and highlight wood as much as possible.
Here's some of the maker spaces tables that were made out of the dungeon material, that 3-ply dungeon material.
Question. Your floor surface there, you said you had an 1.5 like weight chip cotton, or was it something else?
No, this is
The
on
slab.
the ground slab right here. This is polished concrete. Yeah, everything else up above was that 1.5 chipcrete topping on a sauna mat isolation layer on it. And then most of the spaces up above had either carpet tile or LVT on it. All right.
So happy to take any questions. Not promising we can answer everything, but
Yeah, the stair towers, you said something about, you've done those now to a CLT. Is
Yeah,
that, in retrospect, is that, you put the tolerances and everything that you're talking about, is that kind of the right answer in retrospect, or is it more still case by case?
I think it's case by case.
Yeah, both are valid, I guess.
Yeah, there's a lot of pieces to that. Not only does the university have concern about a means of egress, life safety egress stair being out of a combustible exposed material, the AHJ also had an issue with it. And there's an assembly where you can use the CLT and wrap it with chipboard, so you leave nothing exposed, and you can have a tested assembly. But I don't know, economically that probably didn't make a lot of sense.
It didn't, and it was an economic decision and an authority having jurisdiction decision too, but I'll tell you from a constructability standpoint, we talked about it several times that, you know, as it went on and reflecting later on, it would have made a lot of difference with those tolerances. I mean, we fought that a lot. And we had a really good concrete tower placement, and we still fought it. So that would have solved a lot of problems. Yeah, the wood stuff was spot on.
You mentioned having to use aggregate piers. Is that because of soil condition or just the extra mass of this?
It was a soil condition. It was a soil conditions. Actually, the mass of the wood, the weight of the wood is less than than it would have been with the traditional structure.
Significantly
Yeah.
less weight, yeah.
Yeah. And they also did some things. at one time, they were considering a lot more brick veneer on the outside of the building. They do still have some at the base, but those mooring panels, the metal panels on the upper floors was not the original design on that. It was going to be brick, but that reduced some of the weight too. But yeah, it was just a soil enhancement. I think the structural engineer, if I'm getting these numbers right, it was spread footings. Everything was placed on spread footings, and the amount of the cost of the spread footings, the local engineer estimated we saved about $1 million. I think it was like 1.2 million on the size of the foundations because of the rammed aggregate piers, because of the enhanced bearing capacity. What those rammed aggregate piers do, if typical soil will support 2,500 to 3,000 pounds a square foot, the rammed aggregate piers increases the bearing capacity of the soil to 7,500 or 10,000, and so it reduces the size of the footings. And I think we spent about $600,000 putting those rammed aggregate piers in, but the net gain was like $600,000, $500,000 to $600,000 savings because of the savings in the foundations. Thinking I'm getting those numbers right. Yeah, and they went really quick. The rammed aggregate piers, they go really quick.
Go ahead.
Was the problem that you had with, or the difficulty that you had with the multi-story columns, was that something that the manufacturer hadn't anticipated that would be a problem? Or they kind of, that's your problem? Or
I think the latter.
Okay.
The multi-story columns and it seemed like a lot of the things that the manufacturer, the connections, these plate connections, and it was really written into the scope of it being installed in the shop. They've got the capacity to do that, and it goes real quick. But the shipping problems related to that. The things those things that happened during the discussion of how things were going to be fabricated with the multi-story columns and the connections and stuff, all ended up having a significant impact on the ground for us. I don't know. I don't know that it was the wrong answer. It was a frustrating thing to deal with. Once we had to deal with it because it was not anticipated. But
and they weren't really able to help you determine that.
I don't. I don't. If they were, they didn't.
Okay.
Yeah. And it's again studying those things out and really knowing where just that one detail of that column splice occurring within the floor plate was a major thing. If it would have happened, typically when you have steel splices, they occur like 2 or 3 feet above the floor slab. And but that stuff all gets covered up too. In this case, all this stuff is exposed, so they didn't want any of the splices didn't occur. Within where they were exposed, they were concealed in that floor plate. Just something like that. Once you saw it and realized what you were up against, you said, "Uh-oh, man, this is really going to be hard." And again, a lot of these things, and I'm not, hindsight's always 20/20, but with the condensed time frame for the design team, and then getting everything fabricated and getting on schedule, we were really condensing and reducing decisions down to. They were on the fly. It was like, we've got to get this thing in the shop and get this material going and get it fabricated. And, in a lot of cases, if we would have just had another few weeks, to really think it out and digest, what the impact of some of these connections were. I would like to think that would have made a difference and brought some clarity to the decisions that were made, but we made a lot of decisions really fast, and most of them were good, but there was a few of them that fit us.
I think just the layout of the building and the shape of it and the linear nature of the building kind of helped us. It was played to an advantage in that we were literally we had some, fabrication panels, being fabricated while we were still working through coordination and clash detection at the other end of the building. So it was kind of this linear process of sequencing.
Yeah.
Which helped us out.
And we even learned some things going through on the biggest, the biggest wing was B wing. It was the one down the hill that was C-shaped, and then the upper one was the A wing, which was L-shaped. And we did the C-shaped B wing first. And a lot of the things that we learned on B, we implemented on A. And we were able to actually shoot some of the stuff, some of the structure on A was up in place in time for us to actually shoot, the actual locations and laser scan, shoot all that stuff in and know what we had before the wood pieces were fabricated and bring over to that. And that was ideal. That helped a lot, as well as just, some of the things that we learned in B. So to Greg's point, that helped a lot where you could be actually fabricating, something while another piece was being built.
What was the fabrication and the time of shipping?
Once they pulled the trigger, it was into the shop. They had it fabricated and shipped and on site in about 12 weeks. It's really pretty fast. Yeah. But it was all that, it was that 6 to 7 months up, pull the trigger and get it in the shop that was the key.
Awesome. Any other questions? Congratulations, guys. It looks like a great project. Really appreciate you coming in and talking to us about it. And it's always a little nerve-wracking to start with a new construction type that somebody isn't an expert on in your group. And so congratulations. Thanks again.
Thank you.
Gentlemen, thank you so much. Thank you. Great presentation. Great project.
Thanks for helping
Pretty
set it
excited.
up.
Yeah, anytime. I'm sure you guys are going to have more than one, not necessarily presentations, but projects. Now that you have it dialed in, it's like, oh, we can do that. We'll do that. But I'm trying to convince somebody. No, we really ought to look at doing this. It's kind of scary because as a designer, it's like, we can really do this with engineering. Cheaper, faster, and we'll have it done. So to take that risk and take it on, that's really cool. So congrats, it's neat.
So I have a question to ask before I head upstairs.
Yeah.
How did the Arkansas timber business feel about the fact that everything was shipped from Australia?
Oh, well, there's